not constant rate production, not pseudo-steady state, where the pressures are all kind of sinking at the same rate. And the rate equation that we had originally looked at was something like this, and we're going to do it for gas. So we've got pseudo pressure average volumetric minus pseudo pressure at the bottom of the well, flowing bottom hole pressure, and you guys can't see what I'm trying to do here, but and then we had reservoir temperature. And this outer boundary RERW. And since we use average reservoir pressure instead of initial pressure, we have to have this minus 3/4 here. We have talked about skin. Looks something like that. So this is our pseudo-steady state or boundary-dominated gas flow rate equation. And the pseudo pressure is this integral like that, which has a graphical representation kind of like this. And it's kind of a straight line, starts curving over, and then it kind of becomes a little bit flat with a decreasing slope. So that's the pseudo-steady state equation. And so what we talked about was setting, kind of using the same type of formula and thinking about what would happen before the outer boundary is reached. And you can kind of think of that as the external boundary getting bigger and bigger. So any questions about that? I mean, it's not pensum, but I mean, if there's any lingering questions from the lecture on Thursday, now's the time to take it, because we're not going to revisit that very much. Any questions? Okay. Now, so this is our pseudo-steady state equation, or what we also call boundary dominated. Basically, this is a function of time, the average reservoir pressure because of the depletion, and everything else is essentially a constant, but because that's a function of time, the rate is a function of time. And it's a very slowly varying function of time because the average pressure hopefully won't drop very quickly. In the Fetkovich paper that you should have been reading, he also talks briefly about the infinite acting condition, just very briefly. And I wanted to pull up that paper, which is why got stuck here, handouts. This is the paper. Okay, this is an equation. It's just written in a little bit different form, but it's got this. Forget about this stuff over here. But this this term here, 1/2 log TD plus 0.809, is treating the infinite acting for radial flow. And in that case, the dimensionless pressure this equation looks just the same, except now we use pseudo pressure at initial conditions, which is a constant, minus flowing bottom hole pressure, pseudo, and that's a function of time. TR and the pseudo pressure, I'm sorry, the dimensionless pressure instead of the log RERW. Man, give me a break. Plus S. Okay? And this PD here for radial flow is given by, well, on Thursday I told you that it starts as square root of time, and then it transitions, and then it gets into radial flow. But for the radial flow part, it's basically 1/2 log dimensionless time plus 0.809, 07. So that's the equation, and you find that in his paper. So that's, when you see that part, that's what he's talking about. We're talking about infinite acting flow before the boundaries are affected. We're talking only about the radial flow period. And this can be inserted in here. We have to change out the average pressure with the initial pressure, and basically we get, this is for constant, this is for a constant rate. So basically you've got, this is a function of time, and this is a function of time. And this is constant now. Okay? In order to get something on the left being constant, you've got the bottom of flowing pressure changing with time, and it's correspondingly on the bottom the dimensionless pressure. So these are equivalent equations, except for this is boundary dominated, this is infinite acting. He talks about both of them. And the point I want to make here is that for this first equation, there's only one constant, okay? And in theory, that constant, which I'll circle with red, that constant is here. So that's a constant. Okay? It includes this all-important permeability, thickness product, reservoir temperature, and the geometry and potentially some skin. Now in theory, that constant is constant forever, for all times, for any time greater than 0. Should never change for a gas well. The reservoir pressure will change, and accordingly the relationship between gas rate and PWF will change. Okay? But if you take at a given point in time, when you know the average pressure, you know the relationship between QG and PWF. Okay? So let's just draw that. I've gone into the red mode here. That's okay. And often the way this is plotted, it's called inflow performance relation. Inflow performance relation. Any of you foreigners who have had this stuff before, have you heard of the IPR? Yeah? Okay. Inflow performance relationship. And what we're going to plot is pressure versus rate. Okay? And this is for pseudo-steady state or boundary dominated flow. And the curve is going to look something like this for a gas well. Okay? It's curved. This is flowing bottom hole pressure. This is the average reservoir pressure initially. And the reason it is not a straight line is because this equation has pseudo pressure, right? It's not pressure, it's pseudo pressure. And so, in a sense, this higher pressure stuff, we're going from here to here. It's kind of a more or less a constant here, so that would result in a straight line relationship here. But then as this starts going down, we don't keep that straight line behavior. It goes something like that. The actual performance at a given flowing bottom hole pressure is considerably less here than if this function looked like that as a constant, then you would get this relationship between flowing bottom hole pressure and rate. It would be basically a straight line. Okay? But instead we get this deteriorating gas mobility. It deteriorates because of the PVT expansion, and it drops off like that, and then this, basically this loss here, that's due to our PVT of gas. Now, this particular curve that I've drawn here is for time equals 0. Okay? That's time 0. If we wanted to know that constant here, if we wanted to know what that constant is for a given well, then when we drill the well, we could just run a test, right? We put the well on production, we measure the bottom hole flowing pressure, we know the initial pressure, right? Okay? So, to find this constant, you only need a single test. Okay? You need one rate and one bottom hole flowing pressure. Okay? So let's just say that we go in and we do a test here. We draw the well down the first week of the first week the well's on. We get that rate. We control it with this pressure, and with that one point, we're able to determine the constant. KH TR log RERW plus skin. Forget the 3/4. Okay? Now we don't know what the permeability is. We may know the thickness. We don't know the permeability. We don't know the RERW. We don't know the skin, but we know the total constant. And if we don't do anything with the well, that constant will just stay that way from now forever on. It takes a single rate test. Okay? It doesn't matter where you take the test. You could have taken it here if you wanted to. Okay? Doesn't matter. If you'd run the test here, the point would be down here. It's or. You don't need both of them. If you ran both rates, both drawdowns, you should get the same constant. Put it there. We don't care. That's today. And that's generally what they do. They drill the well, they do a production test, they measure one rate, one bottom flowing pressure. They know the initial pressure. When they drill the well, they measure the pressure. So that then they've got the constant for that well. It's supposed to stay the same. After a year of production, the average pressure has dropped down to this level here. Okay? But we can just use the same equation, the constant's the same, and all we do is we just change this average pressure, and we now have the new relationship between gas rate and PWF. And that's going to look something like this. Okay? And at 5 years, be down here. Okay? And by the way, where this reaches zero bottom hole flowing pressure, which is impossible, by the way. I mean, it's not impossible. It's not usual. If you put a compressor at the top of the well, you're actually surprised that you can get a pretty low bottom hole flowing pressure. But this is a theoretical, this is a maximum drawdown, right? You can't draw down the pressure in the well any more than that, as PWF goes to zero. And this rate that you get here is called the absolute open flow potential. Absolute open flow potential. You can't produce more from the well. And it would require putting a big compressor sucking on the gas at the top to bring the pressure so low. And putting in infinite sized tubing, okay? So you'd have a lot of strange things going on, but it's the absolute open flow potential. Sometimes we refer to it as QG max. Yeah.
For analyzing this graph, why we are using pseudo steady state equation? Because at the time of zero, the effect of pressure hasn't reached the boundary.
No, it's to time zero. Let's say the time to pseudo steady state is 8 hours. We calculate it from the stuff on Thursday. The time to pseudo steady state could be 8 hours, it could be 8 days, it could be 8 weeks, it could be 8 years. But I'm saying that it's 8 hours. So if I flow this well for 12 hours, I'm in pseudo steady state. That's what I'm assuming here. So it's effectively time zero plus 12 hours. Okay? The point is that we only need a single rate to get the constant here. And it doesn't matter what the rate is, you can pick any of these. Once you have the constant, you can then draw the curves for different average pressures that will change over time. And you'll know at any given time after 5 years, for example, this is the maximum rate of the well. Let's say that we put in, we've got a pipeline pressure, and realistically, let's say that this is our minimum bottom hole flowing pressure, because you have a pipeline you're flowing into with 200 psi, and you've got some pressure drop in the tubing. So down at the bottom, that's 500 psi. So you're basically, if you flow open to the pipeline, then you'll be flowing these rates here. Now you may have a choke on the well, and you may only produce it, up here. But this is the way you do engineering performance, well performance. How much will the well deliver at any given time? And if Darcy's law, which is the source of this equation, this is based on Darcy's law, If it applies, then we can do it this simple. We make one test, and then we know the well performance the rest of the time. Okay? If the time to pseudo-steady state is 8 hours, okay, then you would have to use this second equation during that 8 hours, okay, to analyze the performance. Okay? The time to pseudo-steady state might take 80 hours. Okay? In which case, then you still have to use this equation 2 for a 12-hour test, because you have to find out what is the PD value at 12 hours. Okay? And you can't do that with one point, because if you take the test at this is being our constant, this is no longer constant. This is a function of time. Okay? So if you put the well on production and you look at the bottom well flowing pressure, it doesn't become constant. It is changing continuously as a function of time. So that's a problem. It looks like the well's PI, or constant, is changing with time. It's a function of time until the time to pseudo-steady state, which we talked about last Thursday. And once you reach that time to pseudo-steady state, then you use this equation here. Where the only time dependence is handled through the average pressure. And that average pressure time dependence is very slow. Now, you might ask, why do you plot it as flowing bottom well pressure on the y-axis versus rate on the x-axis? You're really interested in rate if you change the pressure, right? But it's just convention. It's the old, you can't change it. Just the way it is. For lower perm, the time to pseudo-steady state can be larger. Let's say days, weeks, months, maybe even years. Okay. So in that case, I'm going to make the same plot, but now using equation 2, this is going to be our initial reservoir pressure. This is going to be something like that. And that curve there is going to be valid for at 12 hours. Okay? Let's say that the time to pseudo-steady state for this is 100 days. Okay? So that's a half a day. Using equation 2, we always start from the same pressure here. It's going to be a little bit hard to draw. Now that's going to be for 1 day. One week, and then $100 days, and that's our time to pseudo-steady state. Okay. Now, to come up with the analysis of what is the pseudo-steady state constant, which is really the KH, reservoir temperature, and this term here, you have to take and measure, so to find the KH over reservoir temperature, to find this term here with the log RERW and skin, our PI, productivity index, as they call it. You basically have to run a transient test. You have to measure the rate and pressure during a period. You know, maybe not 100 days, but in theory you could do it over 100 days. But you basically, you might run a test. You have to run a transient test where you measure rate as a function of time and bottom hole flowing as a function of time. You know, the profile might look something like this. You know, the trajectory of that in time might look something like that, so that, you know, at 12 hours this was the rate and pressure, at 1 day, and at 10 days. And you might have some even shorter times, often you do. Maybe this is the point you find at 1 minute. Okay? So you've got this range of bottom hole flowing pressures as a function of time and rates as a function of time. And then what you do is that and to do the analysis properly, you have to use pseudo pressure. You have to take initial pseudo pressure minus this as a function of time over rate as a function of time. This is kind of the what we talked about last Thursday is this rate normalization effect, or the Weinstock and Colpitts guys. And what you'll find is that this will follow some well, if you plot it on log of time, log axis, then you'll get a straight line. Okay? And the slope of this is effectively going to give you your PI number. It's not quite that simple because you have to, it's at least you'll be able to get out the KH of that part of the PI. So this is called a transient test, which gives you a transient. This is basically what we call PI. As a function of time. And then that's interpreted, because we know how that should change, it should change as the log of time. Square root of time here. And this kind of test applies to lower perm. And for gas wells, that would typically be less than about 0.1 millidarcy. Maybe 1 millidarcy. Usually that would be high enough. 1 millidarcy if it's a very high pressure, 0.1 millidarcy at lower pressure. So somewhere in this range. Anything lower than that, you might have to do transient analysis of rate and pressure to come up with the PI or the KH of the well. Okay. This is from equation 2. And that's because equation 2 has this time-dependent denominator. Equation 1 doesn't. Okay? So to use equation 1, this basically can be used when time is greater than time pseudo-steady state. So if during your test, your time pseudo-steady state is less than a day, then it's not a problem to use this equation and use it for your engineering. So that might be for sure for gas wells permeability greater than 1 to 10 millidarcies for sure. 1 day production test, it'll probably be close to pseudo-steady state like behavior. Now this is what I would call a single flow test. The rate is not constant, but you basically you put the well on a constant choke. Okay, this is basically the performance of a constant choke. The flow rate changes a little bit during the test, and the bottom of flowing pressure is changing as a function of time during the test. But we'll call it a single flow test. We just put the well on a constant choke and let it flow for, a day or 5 days or 10 days or whatever. And we monitor the pressure and rate. And that basically allows us to come up with the constant KH, which is the most important part of this pseudo-steady state rate equation. The KH is the biggest, most important term. Okay, any questions? So we've got a basically in both cases we're going to run using a single choke, but if you have a high enough perm, you put it on a single choke, the rate's going to stabilize to more or less a constant value. You get the bottom of flowing pressure is going to be more or less constant, and you get your PI directly. Okay, if it's a lower perm, you put it on a constant choke, the rate's decreasing somewhat, the bottom of flowing pressure's decreasing somewhat, and you have to do this, what we call transient analysis, to come up with the PI or the KH. Okay? Again, equation 2 is based on Darcy's equation, Darcy's law. So, we're going to take a break, but after the break, what we're going to talk about is why this paper is called the multi-rate testing of gas wells. Okay? Because the tradition, way back then when people were in the old days and today, that's what we do with gas wells. We do multi-rate tests, which is effectively running the well at multiple choke settings and multiple choke settings. We're going to talk about why we do that after the break. Okay?